Check this out. We've got something really fun today. This is so amazing. Oh man, again? 8.3 Logarithmic Functions. This lesson is going to be a review of the logs we were doing in Math 30-1. So what is log base 4 of 64? Well, we think 4 needs what exponent to get to 64? And it would be 4 cubed is 64, so this equals 3. 1/4 needs what exponent to get to 16? Well, we need to give this a negative exponent so that we take the reciprocal of it, and then it would be 4, and we just need 4 squared to get to 16, so this would be -2. Now this one we're not going to get a numerical value, but we can use our log laws here. If we have an argument and it's raised to an exponent, we can take that exponent and drop it down in front as a coefficient. And then log base b of b is just equal to 1, because b to what exponent gives me b? 1. This down here, we can introduce a new variable to help us with this one. If we don't remember what this one is, we could say this equals y, because y is not used anywhere else in here. Now we could consider this as something written in exponential form, and we could rewrite it into log form with this as our base. So I will say log base b, that would be this base right here, and there's the argument of the log function, and that would equal the exponent goes on this side of the equation. And now we see that everything's the same, so y must equal x, so this just equals x. So that's a good thing to remember if you have this scenario. This one here, the log law, if we're adding two logs and they have the same base, that would be the log of a times b. And this one here is just to help you remember that if we're subtracting logs with different bases, then we don't have a log law for that. We could change the base and make this look different, but not really any simpler. So we could say maybe we like base 3, so this one's okay. And we could change this to base 3, so log base 3 of 3, and log base 3 of the old base in the denominator. And this equals 1, and at least we could change it around like this, but nothing to do to get them together here. We could have changed it to base 5 or even base 10. We want a good idea of what log graphs look like so that we can do our limits. Let's graph f of x equals log base 10 of x in blue. And we know that there'll be an x-intercept here at 1. The next good point we could consider would be at x equals 10, because that would be y equals 1. But that's off our graph, so when I'm drawing this, I just can't pass y equals 1 as I come off this side here. And I also know that it's a log function, so it has a vertical asymptote here at x equals 0. So my function will come up here and then head this way here. And let's do the domain of f of x before we move on. Do that in set builder notation, so x is such that x is any real number greater than 0. And the range is just any real number because it continues on forever. Let's switch colors to green and draw the green graph h of x. And this one is a base 2, so it's not a transformation of this graph, it's a completely new one. Now looking at this, it might be easier to solve this one for x instead. I'll show you what I mean. So right now we have y is equal to negative log base 2 of x and plus 2. So I'm going to subtract 2 So we got y minus 2 equals negative log base 2 of x. And divide by negative, so that will give me 2 minus y instead, equals log base 2 of x. And there's my base, there's my exponent. I'm going to rewrite this into exponential form and get x equals 2 to the power of 2 minus y. And then it will be easier to pick values of y as opposed to some value of x that I can actually calculate, although not impossible here. So I'll make a table of values here, and I'll be picking y values, but I start with 0. So when y is 0, looks like x is 4. And that would be right here on the graph. When y is 1, then it looks like 2 minus 1 is 1, so x is just 2. When y is 2, we get an exponent of 0, so 2 to the 0 is just 1. And maybe even 3, y equals 3, that would be 2 to the negative 1, so that would be a half. That's probably good enough to get an idea of where this is. So we've got 2, 1 here, 1, 2, and 1 half and 3. And looking at this, looks like all my x values will be greater than 0, still has the same vertical asymptote here. So this will come down here, and that's through this point, and keep going this way here. And I'll draw that vertical asymptote on there, since it's for them both. The equation of that would be x equals 0. Let's do the domain and range for h of x in green. So it looks like x is also any real number greater than 0. And the range is, what do you know, any real number. And since I've got two graphs on here now, better label this one as h and this one as f of x. The natural logarithm is when our base is e. That's our irrational constant, 2.71, that we talked about previously. And it's so common, it gets its own notation, ln. And so you don't need to write log base e. We write ln of x. Now, some people call this ln or ln, or just logarithm natural. But if we rewrite it into exponential form, that's what it would look like. Let's solve these ones here for x. So our base is e, and our exponent is 4, and it would be x equals e to the power 4. This one here, let's use log form. So here's our base, and I'll just use the natural log of 6 is equal to the exponent here, and I just need to do a bit more algebra to solve for x. So we'll subtract 4 on both sides and divide by -3. So we'll just put this in brackets just to show that the -4 is not in the log function. And divide by -3. And this is fine, mathematically great. I just don't like the negative sitting there, so I'm going to switch this up and say, how about 4 minus the natural log of 6 all over 3. We want to find the domain and sketch f of x, which is the natural log of x cubed minus 8. So this isn't quite a review because we didn't put cubics inside a natural log function before, but we can use our knowledge and figure this one out. So first of all, the natural log is just like any log. It needs a positive argument here. So we'll say x cubed minus 8 needs to be greater than 0. And plus 8 on both sides, and the cubed root of both sides, and we get that x is greater than 2. And so let's sketch this. Draw some axes here. And here, this would be my y and x. And we've got a vertical asymptote at 2. So 1, 2. And our graph needs to be greater than that. And there's no vertical reflections. So this graph comes up from below and goes this way here. And this would be our f of x. Let's find the limits of these logarithms. So the limit as x approaches negative infinity of the natural log of x squared minus 9. First, let's just think about where this quadratic is going as x approaches negative infinity. It's got a positive leading coefficient, so it opens up. So as it goes off to negative infinity, this here, this quadratic, goes to positive infinity. Now, if this goes to positive infinity, then what's the natural log of positive infinity? And that would be infinite itself, and therefore we can conclude that the limit does not exist. Let's try the next one. So here we have the limit as x approaches 3 from the positive side. So if you need a little reminder of what that is going to be for this quadratic, we could sketch that. We've got a positive leading coefficient, and x-intercepts at positive and negative 3. So there's negative 3, there's positive 3. Looks like we're coming from the positive side. So we're coming this way, and that means that this quadratic inside here is getting closer and closer to 0. Now, then we want to determine what happens to the natural log as its argument gets closer and closer to 0. Now we think of the natural log function, and that looks like this. And as we get closer and closer to 0, we follow this graph down, and it approaches, or it goes off to negative infinity. And that's some useful information if we were trying to sketch this, but as a limit itself, that does not exist. How about this one here? So the limit as x approaches 2 from the positive side of all of this. So let's get a sketch of what this looks like here. So we've got, we might want to factor this. Maybe that would be easier to plot on this graph. So we've got, take out that negative because that's annoying. And then we can say x plus 5, x minus 2. So that means we've got an x-intercept at negative 5 and an x-intercept at positive 2. And this has got a negative leading coefficient, so it opens down. So that's a rough sketch of my quadratic argument here. We're going to approach this 2 from the positive side. That means that we're going to be in negative territory. And since this is the natural log, then we can't have a negative argument going on in here. And so this is, let's see, this right here is outside the natural log's domain. ln's domain. So this one just does not exist. It doesn't go to positive or negative infinity. It just doesn't exist at all over there. And last one here, we've got the same quadratic inside the natural log. This time we're approaching 2 from the left. So we're coming this way. And that'd be similar to what's happening up there. Getting closer and closer to 0. So the natural log, as it gets closer and closer to 0, starts heading off towards negative infinity. Therefore, we conclude that this limit also does not exist. Hopefully you can evaluate logs without a calculator, find their limits, and visualize the basic log graphs. There's some questions. Give them a try. See if you know what you're doing.